All right, so last time we defined dot product and projections. Okay, dot product of two vectors in Rn is defined by this formula. You just multiply coordinates term-wise and then add them up. So in R2 and in R3, they are given like this. We did one example, and we see that for a vector u, its dot product with itself is nothing but its length squared. And then we gave this theorem, which states that the dot product of two vectors can be also given by this formula, namely norm of u times norm of v. So length of these vectors times cosine of the angle between the two vectors. And we gave this proof, which is basically cosine theorem for triangles. Okay, so let us continue. What about projections? Or maybe before I proceed, let's do one example. Okay, let's find the angle between okay, the vectors, just vectors. Let's say u is 2 minus 1 3 and v minus 5 minus 2 and let's say 0. So we know that u dot v is just norm u norm v times cosine theta, right? If these are the vectors u and v. So from this cosine theta is just u dot v divided by norm u norm v. So in our case, these are the vectors, and then you take norm of this, pardon, and norm of this. So this is just minus 10 plus 2 and 0, and then norm of this 4 1 and 9, right? Length of this vector, and then length of this 25 plus 1. So this is minus 8 over root 14 times root 26. So therefore theta is just cosine inverse of minus 8 over this number, whatever it is, 14 times 26 in square root. Okay. Let's also talk about projections. So what's the projection of a vector onto another vector? The scalar projection of a vector u in the direction of a non-zero vector u is defined by the formula şöyle s u dot v divided by norm u norm v, and then so this is just, since this is norm u norm v cosine theta, it is equal to norm u times cosine theta. So you may either compute it this way or this way. And what is this? If you look at this okay, let me say it this way. Suppose this is the vector v and this is the vector u. So the projection of u along the vector v is the following. You look at the angle between them and then just cosine theta times length of this. So it is nothing but just the length of this vector. Okay, so that is the so length of this is just s. Okay, this length. Yani u vektörünün v doğrusu üzerine aslında dik iz düşümü, değil mi? So suppose you have this right triangle here, so it is nothing but the length of this side, the red side of this right triangle. Okay, orthogonal projection of this vector onto this line. Okay, thank you. Okay. All right. So this is the definition. Okay, this is the definition, but u dot v can be computed this way. Therefore, it is equal to this gadget. And once we have this, we see that it is nothing but the length of this right triangle, right? Okay. Fizikte falan zaten bunları görmüşsünüzdür, değil mi? Bence istatistik... Efendim? Anladım. Okay. So let's see one example. Okay. Find the projection of u 2, 3 minus 5 along the vector v, let's say minus 1, 1, and 2. So let's say this is the vector v and this is the vector u. We would like to find the projection of u along v. So just the length of this vector. So what is that? S is just u dot v by definition, right? U dot v divided by the length of v. U dot v divided by the length of v. I don't use the cosine theta version of this because I don't know the angle anyway, right? This is much more practical. So what is this? 2, 3 minus 5 dot product minus 1, 1 and 2 divided by length of this v. Well, it is 1, 1 and then 4, right? Sum of squares of entries. So what is this? Minus 2 plus 3 minus 10 divided by square root of 6. So this is minus 9 over this. Well, why we get something negative? Length is cannot be negative, but this means the following. The picture I draw actually is not correct. So it should be something like this probably. The vector u, okay, the vector u is in this direction so that its projection, so this is v, its projection is this, meaning that it is in the opposite direction, okay? So, and this s is this number, and the length here is just the absolute value of this number, okay? So it is 9 over, so this length is 9 over square root of 6, and this minus sign means that the projection of u onto the vector v is in opposite direction to v, okay? V is going this way, but it's the projection of u is going the other way, okay? All right, so soru soran var mı buraya kadar? Yazdınız mı? Okay. The next section is so-called the cross product in tree space. Okay. Definition. For any vectors u and v in R3, the cross product which is denoted like this, u cross v, is the unique vector satisfying the following three conditions. What are these conditions? The first one is this: u cross v dot product u is equal to 0 and u cross v dot product v is equal to 0. Dot product 0 means the angle between this and this is 90 degree because it is length of this times length of this times the angle between them. So for this to be 0, either one of these vectors is 0 or cosine theta is 0. Cosine theta is 0 if angle is 90 degree. So it means this vector cross product is perpendicular to u and perpendicular to v. Okay. Second condition, length of this cross product is similar to actually the formula for dot product, but this time we have sine theta, where theta is the angle between u and v. And the third condition is that u, v, and u cross v form a right-handed triad. It means what? I already told you that u cross v is perpendicular to both of them. So let's say if let's say u is like this and let's say v is like this, then u cross v is perpendicular to both of them. Okay, so something like this. Here this doesn't have to be It can be like this. Okay. Şöyle diyeyim. Okay. U, V. Gene şey oldu. Yani şu ikisinin arasındaki açı şey olmak zorunda değil. 90 derece. Ama bu 90 derece olacak. Okay. This angle is theta here. Right-handed triad means as your fingers you take your right hand and put your hand like this so that your fingers goes from the vector u to towards vector v. Then your thumb should be in the direction of u cross v. Okay, right-handed triad is this. Okay, so this definition, of course, includes a claim in that, namely, there is a unique vector satisfying the three conditions. Okay. Uh, of course, that's not a surprise. Why is that? You see, so remark, note that, uh, indeed, there is a unique vector satisfying these three conditions. Neden? Şimdi bakın, bu koşullar ne diyor? Bir kere U vektörü, pardon, U cross V vektörü, U cross V is perpendicular to both U and V. Okay. So U is like this, let's say, V is like this. Therefore, U cross V is perpendicular to the plane generated by these two vectors, right? These two vectors determines a plane, and U cross V is perpendicular to this plane. So it is either in this direction, U cross V, or in this direction, because there is only one perpendicular line to this plane. The third condition tells us that they should form a right-handed triad. So as your fingers go from U to V, U cross V should be in the direction of your thumb. So U is this, V is this one. Therefore, U cross V should be in this direction. So I determined the direction of the vector U cross V. What else do I need to determine U cross V? I need its length. But the length of this vector is determined by this formula. So the length of this is already determined. Therefore, if you give me these two vectors, I can draw U cross V, okay? You first determine the plane generated by these two vectors, containing these two vectors, and then you take the normal direction, and then using this condition, you determine whether you should take this direction or that direction, and then finally this one tells you what the length of this vector is, okay? Hmm. Yeah, but there are two vectors, but I choose one of them. I choose this one. Why is that? Because this one doesn't satisfy condition 3. Okay, as so U, V, and this one doesn't form a right-handed triad, but U, V, and this one determines a right-handed triad. Therefore, I take this one. Okay. Yeah. İlk koşul diyor ki U cross V, U ile V'nin belirlediği düzleme dik olacak. Şimdi düzleme dik olan iki tane vektör var. Birisi böyle gidiyor, birisi aşağıya doğru gidiyor. Hangisini seçeceğim? Onu üçüncü koşul söylüyor. Peki vektörün boyu ne kadar olacak? Onu da ikinci koşul söylüyor. Tamam mı? Dolayısıyla üç koşul e, cross product'ı belirliyor. Peki, this is the kind of geometric definition of cross product, but in practice, how do you compute the cross product? So what is this unique vector in terms of coordinates? You may ask this, and here is the result. If U is, let's say, U1, U2, U3, or I can write it this way, U1 times I, U2 times J, U3 times K, and V, V1, V2, V3, which is V1I, V2J, and V3K, then U cross V is the following expression. Let me write U2 V3 minus U3 V2 I plus U3 V1 minus U1 V3 J plus U1 V2 minus U2 V1 K. Okay. All right. Before I pass to the proof of this, let's see that what is, for example, the cross product of I and J. Remember, if these are the x, y, z coordinates, this is a right-handed triad, right? This coordinates. I is the unit vector here, j is the unit vector here, and k is the unit vector here. So from this, what is I cross j? I cross j should be perpendicular to the xy plane, and it should be the vector should be in the direction of your thumb, right? So it should be k. What about j cross I? Well, this time your fingers should go from j to I, so your thumb should go in the opposite direction. So this is minus k. Just from this, picture, I can write this. What about, for example, j cross k? J cross k. J is this. So j cross k is just I. Therefore, k cross j will be the opposite, minus I. And finally, k cross I. What is k cross I? It should be like this. So this is j, and I cross k is just minus j. Okay. I don't need any formula for this. Just from, geometry, I can do this. Of course, I should check the length condition, but here all of them are unit length, and the angle between them is 90 degrees, and cosine 90 is 1. Therefore, the length of this cross product is what? Length of j, length of k, times sine theta, but this is just pi over 2. So they're all 1. Therefore, this has length 1. And it is in the direction of I. Therefore, this vector should be I. Okay? So for this unit vectors I, j, k, cross product is determined this way. But here I have, of course, a more general thing. Okay. The book has a proof, but I can provide another proof. Okay, using this, so proof uh, assuming the cross product uh, distributes over addition and scalar multiplication, we can prove the theorem as follows. Yani şunu kabul edersek U artı V cross product W'nun şu olduğunu, tabii ki bu da ispat gerektirir ama bir de yani tabii tersini de bir de şu lambda U çarpı bu lambda U cross W. Bu ikisini kabul edersek o zaman bu ispat çok basit. Neden? Note that in this case U cross V nedir bu? U dediğimiz neydi? U1 I, U2 J, U3 K cross product V1 I, V2 J plus V3 K. Well, using these two rules, I can write this. So product of this one and this one, so U1 times V1 I cross I plus U1 V2 I cross J, U1 V3 I cross K, okay, plus, and then I multiply this one with all of them, U2 V1 J cross I plus U2 V2 J cross J plus U2 V3 J cross K, and then this times this, so U3 V1 K cross I, U3 V2 K cross J, and U3 V3 K cross K. Now what are these? Also note the following. Here I didn't write that down, but what is I cross I, for example? I cross I. Well, this should be length of this one, length of this times the sine of the angle between them. But sine, the angle between the vector I and I is just 0. So this is just 0. Actually, this is true for any vector. V cross V, right? This is length of V times sine 0, but sine 0 is just 0. Therefore, this thing is just 0. So V cross V is always 0. Okay. So if I use that, let's see. So this is 0. I cross J is K. I cross K is minus J. Right? Buraya yazdık. I cross K is minus J. J cross I is minus K. J cross J is 0. J cross K is I. K cross I is minus J. No. K cross I is J. Sorry. K cross J is bir dakika. K, A, J. K, J minus I. And K cross K is 0. So what is the result then? If I so what are the I terms? I terms, there are two of them. This one, so U2 V3 and then minus I U3 V2 I plus J terms. There is this one U3 V1 minus U1 V3 J plus K terms. There is K term here U1 V2 minus K term here U2 V1 K. And this is exactly the statement. Okay. So this finishes the proof. Of course, here I made the assumption that cross product is kind of linear. Okay. If you have a summation and then cross product with the third vector, cross product distributes over this summation, and you can take constants out. I did use those assumptions. The book has another proof, but let me just skip that. So this finishes the proof. Let me just remark here. The book suggests another proof. Read it. Tabii kitabın ispatı daha aslında bir yerde complete. Neden? Çünkü o assumption'ları yapmadan yapıyor. Ona da bakabilirsiniz. Örnek yapalım. Mesela şuna bakalım. Minus 2, 3, 1 cross product 4, 0, 4, 2 and minus 3. Well, what is this? Well, the first one actually is minus 2i plus 3j plus k. Cross product, this one is 4i plus 2j minus 3k. Okay. You can use, of course, the formula, but you can also do it this way. So this times this is just 0. So I have just I and j. So minus 4 I cross j. I cross j is just k. And then I have this. -2 -3, so plus k plus 6, I cross k. I cross k is minus j, and then this thing 12 j cross I is minus k, and then this is 0, forget that, and I have this one minus 9 j cross j cross k, sorry, j cross k is just I, and then I have this 4 k cross I is j, and 2 k cross j is minus I, k cross k is just 0. So we have what? What are the I terms? I have minus 9i and minus 2i, so minus 11i. And then j terms, minus 6j and 4j, so minus 2j. And k terms, uh, minus 4, minus 12, so minus 16k. So the cross product is this. Okay. Umarım doğru yapmışımdır. Yani kontrol edebilirsiniz. Okay. Properties of the cross product. Let's list the properties. If U, V, and W are any vectors in R3 and T is any real number, then we have the followings. Well, U cross U is 0. We already saw this, right? Second, U cross V is the same as minus V cross U. So this means the cross product is anti-commutative. Anti-commutative means when you replace the terms of the product, you get negative of the answer. Third one is so distributive law. U cross V W plus V cross W. U cross V plus. So it is distributive in both components. U cross V plus U cross W. Tu cross product V is T times U cross V. So T just goes out, and this one is just U dot U cross V is just 0. And this is also V dot U cross V. Okay. I mean, we already actually assumed these but you can write these down using the component-wise, definition of cross product, right? If you just use actually formula, you can see that it is really the case. U cross V and this is trivial because the angle between U and U is 0. What about this one? If you interchange these two, then the right-handed triad rules tells us that they should be negative of each other because you replace two vectors. So if your hand is in this direction for one of them, for the other one it should be this direction. So it should be just negative. These two, well, I assumed those. You can prove this using the formula of cross product in terms of coordinates. This one also can be proved that way, and this is just actually the condition in the definition, right? It is just this definition, this term, right? U cross V cross U, U cross V dot V, they are both 0. So definition is also stated as a property, but it is just the definition actually. It doesn't need any proof, right? It is just the definition. Okay. Sorusu olan var mı? Cross product'ı daha önce görmüşsünüzdür herhalde, değil mi? Gördünüz mü bir yerlerde? Fizikte gördünüz. Tamam. Okay, there is this remark which is kind of important. So cross product is not, it's an operation on vectors, but it is not associative. It's not an associative product operation on vectors in R3, right? It's an operation. You give me two vectors, I give you a third one, right? Cross product. But this operation is not associative, meaning this. U cross V cross W. Okay. You can take cross product of three vectors like this. First, take the cross product of the first two ones, and then take the cross product of the resulting vector with the third one. Or you can do this. First, take the cross product of the first two, and then take the cross product with the first one. In general, this is not true. In general. An associative product satisfies this, okay, for all UVW, but cross product doesn't. Example is this. Counter example. Let's see. I cross J cross K. And K, no. I cross J cross I. Ama bu oluyor galiba. Bu da minus değil mi? I olduğu için oluyor. Bu olmaz. Başka bir örnek bulmam lazım. Bakayım şurada var mı? Bir tane uyduralım. Ee, Şimdi U ile V aynı vektör olsalar şimdi I cross J e, böyle 0 ama böyle I cross J bu K olacak. Evet. Değil mi? Şöyle yapalım. Şimdi I cross J ile I cross J. Bu nedir? This is just 0 cross J, but this is just I cross K. I cross K is minus J, but 0 cross J is of course 0. So you see, for these three vectors, we don't have associativity. I cross J is not equal to I cross J. Okay? So this product is not associative. All right. Cross product is related to so-called determinants, but let me just explain it on the second hour.